this is what we began with. We spoke of our favorite spider and her favorite fly. And the setting was that she would take a minute to walk along any edge. And the fly, of course, is a dumb fellow. He's just sitting there, spy the fly. And we wanted to find out what spy's life expectancy was. And you remember how we solved it. The way we set it up, we said that the spider could walk along at any corner. She could take any of the three edges with equal probability. So if you did that, the whole thing sort of descends to this very simple sequence of simultaneous equations, one per corner. And you can solve those to decide, to determine how long the fly can expect to live if in this setting, right? Now, as it turns out, there's a simpler way of formulating this particular problem. We're going to encounter that later in class. We also introduced a new class of problems where you are trying to optimize something, but you don't really know whether you've done something good or bad as soon as you've done it. You don't really know whether what you did made sense until much later, like when you play a chess game. A move in the beginning of the game may have doomed you, but you wouldn't know for another 30 moves. Or if you're investing. In 1995, one of my friends wanted to sell me 1,000 shares of Apple stock at slightly less than $5 a share. I didn't have $50, leave alone 5,000. But if I had a time machine, I'd go back and buy, right? Back in the day, it seemed very foolish. It seemed like, it was a lost cause. Or things like this. You change lanes, you know what? You may be doing something that looks locally wise and just end up causing a traffic jam. So you can't really know whether your immediate moves are going to benefit you or make things worse until much later in the game. So all of these are reward-based problems where the common theme is you have some control, you take some actions, and your actions beget rewards. You may win the game, you may make money, you may get home sooner, but not deterministically, because the world out there is not predictable. And more importantly, you won't really know whether what you've done was useful or not until much later. So we had this cartoon of the world. You, the agent, operate in an environment. The environment is the game, the market, or the road. You take some action, and this affects the environment. So the first thing that happens is that you take an action. This affects the environment, which changes as a result of your action and affects your situation. Somewhere along, it also gives you a reward. So given all of this, how must the agent behave to maximize the rewards that it gets? And the reward could be incremental benefits that you get in the stock market, or waiting all the way to the end of the game to win the chess game. So we defined a state which captures the status of the system. So in an automobile, the state of the automobile is going to be the combination of the position, velocity, and the acceleration. If you know these three, you know a lot about pretty much everything that you need to know, at least in a very local sense, about where the automobile is going to be in the next moment. But in traffic, you need to know the position, velocity, and acceleration of every single vehicle on the road, not just yourself. If you are playing chess, you need to know the entire chessboard, where every coin is, and also who gets to play the next move. That's going to be the state of the game. Now, in a chess game, regardless, if you eliminate personal biases from the game, the arrangement of coins on the board completely decides the future. So this again is the state of the game, which decides the future. So in this we define the notion of a Markov property, where a well-defined state fully captures all the information needed to predict what's going to happen next, like in the case of the chess game. So imagine playing against someone, and you start off with a chessboard. Then all you're really interested in is what is the configuration of the chessboard right now, not how you got there, because that's going to decide everything. So the state of the game completely decides the next move. No additional information about the past is required. So this meant that the probability of a state given all the states at all previous times is just the probability of the state of the next time given the current state. And we saw that Flider, the spider, was following a Markov process. But then we also encountered this glider, Flider's brother, who didn't like to turn back. So clearly in this, there was this apparent situation where how the spider ended up at a corner decided where the spider went. So this seemed to violate the Markov decision, the Markov property, which said where you go depends only on where you are and not how you got there. But then we saw that if you actually recast the problem slightly differently, that if you define the combination of the state at the previous time, of the corner at the previous time and the corner at the current time as your state, then the whole thing became a Markov process all over again, right? So all of this we went through in the last class. So in order to facilitate analyzing our problem, we figured that we're going to model our environment as being truly Markov. The environment's future only depends on its present. Now, here within this setup, the agent has to maximize its ability to obtain rewards. So in order to do this, the agent has to know all about the environment and all about the environment's dynamics. And so the agent is going to model the environment. And what we mean by modeling is that it formulates its own internal notion of what the environment is like. And this must ideally match the true values in the world as closely as possible, because only then is the agent really properly aware of its environment, and only then can the agent really act most rationally. But it's going to try to do the best it can. And we also saw examples where how the agent defines the state based on what it has observed can vary regardless of what the real situation is. So in the process, we also define the notion, we formalize the notion of a Markov process. A Markov process is a random process which has a number of states that it can be in. The number of states can be infinite. It can be a discrete set of states. It can be a countable infinity of states. It can be an uncountable infinity of states. All that is characteristic is that there is a set of states that the process can be in, and then there is a set of transition probabilities which says, given that the process is in a current state, what is the probability of it being in any other state at the next time? So for example, for the spider, given that the spider was any given corner, there were only 3 other corners that it could go to, those that connected to it. So that defined the transition probability, right? And all of these you recall. And we also saw that we can define the transition probability as a matrix where each row specifies the set of transition probabilities for a given state. Now this of course only holds if you have a discrete set of states, otherwise you're going to need a function, right? So you recall all of this. Anybody who doesn't recall any of this? I guess not. So can someone follow Piazza, please, just in case somebody is on Piazza? Right. Okay. Yes. There's my pointer. Just thank you. Yes. My laser pointer is lost, so I need something to point to the board with, right? Okay. So this we've seen so far. Now, and we also figured out what the state transition probabilities for this situation were. And then we moved on to a notion of a Markov reward process. A Markov reward process was an upgrade over a standard Markov process. And the upgrade was that now each corner, each state wasn't just an entity by itself. When the agent arrived at any state, it could get a reward. So every state had associated with it a probability distribution over possible rewards, and the reward that it actually got depended on the state that it arrived at. So in our spider the flider the spider example, if this was a Markov reward process, then you would have some swarm of flies at every corner, and any time the spider arrived at any corner, it got to grab a fly. So going to any corner could give it a reward, which could be 0, which could be negative, or which could be positive. And so using that analogy, was this a Markov reward process? Remember? Anyone? Shankai, I see you nod your head. So was this a Markov reward process?
Yes.
Yes, thank you. Why?
Because at each state you can possibly get a reward.
Yeah, you can get either a 0 reward or a 1 reward. So it's a Markov reward process. Please answer me, folks. Otherwise, you're going to slow down the class, okay? And now, so in order to formalize this notion of having rewards, we defined a Markov reward process, which was an extension of a Markov decision, Markov process, Markov random process, which had as its complete definition a set of states, a transition matrix between states, and then you had a reward function which gave the agent a reward at every state, and the reward function was state specific. The way we defined it was a probability distribution over rewards for each state. When you arrived at a state, there was a distribution, it picked up a reward from that state and gave it to the agent. And we also defined something called a discount factor. This discount factor was this mysterious new entity that we didn't quite understand, and so we were still trying to figure out what the heck this thing was when the class ended. So let's go back and revisit the discount factor, right? First, so here's my little cartoon of Flider the spider and many flies. Each corner now has a reward function. So what is the reward function over here? It's the probability distribution over flies at each corner in this figure, in this cartoon, right? So regardless of which corner the spider arrives at, it has a probability of getting a reward. Now, when the spider arrives at a particular corner, it gets one shot. It's going to grab one reward from the distribution. So what it gets in a particular pass through a corner is going to be one fly. That would be one sample from the distribution, which is very different from the expected reward at any corner. So what is the difference? Again, this is going to come back to be important. What is the difference between a sample reward and an expected reward? Over here. Anybody? Akash?
Expected reward is how much you expect to get over time, I think discount factor.
No. Anybody else? Guys?
What uses the probabilities of each.
So the expected reward, so if you have what is the expected value of a Gaussian random variable, which is with 0 mean? Okay, say it aloud, guys, everybody. What is the expected value of a Gaussian random variable with 0 mean? Say it aloud, everybody. 1, 2, 3, go.
0.
Thank you, right? What would a specific sample be? Could be anything at all, right? So in this case, what is the expected reward at any corner?
Probability of each of the samples times the reward for the particular.
That's going to be the mean, right? Just the average. The average is going to be the expected reward at every corner. And but in any given visit of a corner, is the spider going to get the expected reward? Highly unlikely. It's going to pick a sample, right? But the sample is representative of the expected reward in the sense that if you go in and if you repeatedly keep getting fat flies in a particular corner, you can expect that the next time you go there, you're going to get a fat fly, right? So the sample is kind of representative of the expected reward. Now, so let's sort of extend our little Flider the spider analogy. Now, Flider hasn't quite landed on the room. He's hanging from, or she's hanging from a cobweb up in the sky, and has the choice of landing at 1, 2, or 3. And I have given you the reward distributions at all of the corners in the figure. Which of the 3 corners? So she's going to land and she's going to begin wandering using the transition probability matrix that we used earlier. Okay? Which of the 3 corners would you recommend for her that she should land on? 1, 2, or 3? 3? Why? Pardon me? It's close to 4. So what was the rationale you were using?
In the future, what's the possible?
You are looking at the long term. You are not looking at the immediate reward, right? If you were looking at the immediate reward, where would she go? She has a much greater probability of getting something at 2. It's a much bigger swarm of flies. There are far fewer flies on 3. But if she lands in 3, she has a much greater chance of going to 4 immediately, right? This is a very nice, simple system, but what you are really saying is that you need to know the long-term consequences of arriving at a particular state to assign to get some notion of how good that state is, right? And here the long-term consequences seem to be, to you, that landing at 3 is better than landing at 1. Why did you do that? Why did you decide that? Anyone? Just distance? Transitions, you forget the transitions. We assumed all transitions were equally probable. Is that really the case over here? This corner, this box is missing an edge. I didn't tell you that this was the same system as the one before, right? In other words, you don't know that you gave me the correct answer. You just guessed. So in that situation, do you still stand by your answer? Do you still think it's better for her to land at 3?
Depends on your goal. I mean,
She wants to feed. She wants to become fat.
she could just roam around forever. It doesn't matter where she lands.
Really? But then, think about it, that in the big picture, eventually, some places she's still going to get much fatter than the others, no matter how far you get, right?
Depends if there are finite flies or not.
Assuming it's a distribution, you're going to keep drawing from them. You're picking on some interesting points, but we won't address those in this lecture. So again, here's the point. Here, you don't know the transition matrix. If you're spider the flighter the spider, what would you actually have to do? How do you decide? So I'm going to simplify the problem for you. Okay? I'm going to say that she's allowed to practice. One run, she's allowed to practice once. So once she's allowed to land on 1, once she's allowed to land on 2, once she's allowed to land on 3, and run around for a while. And after this, we yank her up and pull her back up, and now she has to decide, based on that one practice, where she's going to land. What would she do?
Do we know the transition probability?
I'm not telling you. We don't, right? So that's where the business of practice comes in, right? So I've dropped her. I've given her one chance to land at one of these corners and wander around. And based on this practice, she has to come up with an idea of how good each of these corners are. So how would she do it? What is the mechanism going to be?
Sample from each of those nodes.
Sample, no. I mean, what does the spider do in my example? She must use her practice to assign a value to each of the corners, which is to say, based on her practice, she must guess how much food she would get in the long term from each of the corners, right? And the way she'd do it, when she's practicing at 3, you're going to drop her, she falls down on 3 and begins wandering around. So she wanders, she starts off at 3, she gets at time 0, she gets a reward R1. Then she's random, right? She's just wandering around randomly. So then she goes to R2. And then she gets to corner 2. She gets some reward R2. Then she goes down and goes down to that corner over there. She gets, I've got my, yeah. So she goes that way and then comes there, R3, R4, R5, R6, R7, R8, R9, 10, 11, 12, 13, 14, 15, 16. So she just wanders around. As she wanders around, at each corner, she is going to get a reward, right? And so she tells herself, okay, I landed at 3, and here's what happened. I got R1, R2, R3, R4, R5, R6, okay? So this is what she got when she landed at 3. So what was the total, how much food did she get this one try? The sum of all of these, correct? But then, is this value representative? Can she believe that this is the value that's representative of what will happen the next time she lands at 3? Remember, I told you that a sample from a distribution is kind of representative of the expectation of the distribution, right? So is this value representative of what she can expect will happen the next time she lands at 3? Yeah? Who says yeah? And who say no? So why no?
I think one sample is not sufficient.
That's not, no, we said that one sample is representative of the mean of the distribution as far as we're concerned, right? I'm giving you that constraint. I'm giving you that, not a constraint, but I'm giving you the extra. Here's the point, there's still an unknown, right? What happened was R1 is definitely representative of what she is going to get the next time she lands at 3 immediately. But what about R2? R2 was not deterministic. She had 3 choices to make. She picked one. Is she going to do the same the next time? Nope, right? What about R3? How many choices did she have? 9. Is she going to pick the same one the next time? No way, right? So as you go further and further out, these things become less and less and less representative. By the time you're out there, there's no way at all that you can claim that what happened at step 16 is going to happen again the next time she lands at 3, right? So her practice run, she has to account for the fact that the future, starting from the point where she landed, was not deterministic, right? So she still has to assign, but then it's not like she can simply throw these values away, right? It's clearly practice. This is information that she must use. So what can she do? Here's what she can do. First, she knows that R1 is somewhat realistic because it is obtained from corner 3. R2, she had a choice of 3 corners. She chose one. It's unlikely that she's going to repeat it the next time. R3, 1 of 9 corners. So highly unlikely that at R3, even if R3 is representative of the distribution it came from, meaning if all of the distributions were deterministic, all of them had only one fly, R3 is still not representative of what will happen the next time, right? Make sense to you guys? So how do you account for this? Yes? I use a discount, okay? So what I will do is this. A better guess to decide how good it is to land at 3 is I'm going to say R1 plus some A1 times R2 plus A2 times R3 plus A3 times R4 and so on, right? Where A1, so as the index increases, you expect the value of A to decrease. Because something that happens far out into the future doesn't really tell you very much, does it? Right? So you expect these discount factors to be between 0 and 1, and you expect them to fall off with time. Make sense to you guys? Right? And so, because you trust the readings from farther in the future less. And what's a good value for these discount factors? It turns out any sequence of A's which falls off with time is a reasonable guess with one constraint. We'll get to this constraint later. But for mathematical reasons, this guy here just happens to be very convenient, that it falls off exponentially. It's pure convenience, nothing else. There are many other ways of modeling the sequence of A's. All you're trying to capture is the fact that your practice run doesn't really tell you very much the further out you go into the future. Make sense? Right? And so that's where the discount factor comes from. And so the discounted return is going to look like this. I'm going to call this, I'm introducing a new term. I'm calling this a return. So I'm assigning some value, I'm assigning a number to the corner. How good is it for Flider the spider to land at corner 3? How good is it? Think of yourself as an investor. If a fly is investing into its future, it's going to count returns, right? And it's going to do one practice run, and that practice run is going to give it some idea of what the return is going to be at that corner. And so it's going, but then because it keeps discounting the future, we call it the discounted return. And that discounted return gives it some notion of how good that corner is going to be. So what would Flider do in our example? She's going to land at 1, she's going to do a run through. She's going to land at 2, she's going to do a run through. She's going to land at 3, she's going to do a run through. She's going to compute a discounted return from each of these 3 corners. And then the next time around, which one will she choose? The one with the highest discounted return, correct? So here's what it is. Now, this discount factor gamma is our belief in the predictability of the future. So which means, if Flider had infinite choices and randomly picked one, then the odds that she's going to pick that again are practically 0. At that point, you're not going to believe the future of this particular trial run at all. Your gamma is going to be 0, right? At each point, there was only one thing that Flider could do. Then that sample sequence is representative of every time you're going to do this thing. In that case, you're going to choose gamma equals 1. Not so easy. There's a little more to it. We'll see that in a few slides, okay? So observe something very strange here. The return at time t. So here, I've got gt, right? In our example, what was time? So in our example here, we started at time 0, but then started counting rewards R1. At time 0, she lands at the corner, and then she gets reward R1. Then she makes a transition at time 1, she lands another corner, but she gets reward R2. So this is just an indexing mix-up that is common in this particular literature. We could have started counting at R0, and the math might have been easier. So wherever I picked up these indices from had an odd indexing scheme that I'm keeping, okay? But the point is, here is the point, right? Now if you expect that the cube isn't changing, then so here's something very interesting. If you go through the process, you can always say at time 0 I got some return, but then as this fly kept going, right, she walked for 7 steps, and then there was a future ahead of her. So that was the return at time 7. So you can always speak of the return in terms of gt. And so gt is going to be the reward, immediate reward, which strangely enough has an index t plus 1, plus gamma times the reward of the next instant, plus gamma squared times the reward of the next instant, and so on. So that's going to be your discounted return at time t. So this clear? So now, again, you can ask yourself, I've actually seen these samples. Why the heck am I discounting the future? We're getting back to the fact that there was uncertainty in the future. The process, the underlying Markov process itself was not deterministic. We are not speaking of the sequence of rewards. You're dealing with the uncertainty in the underlying Markov process. That's why you're discounting the future, okay? There's a second reason for discounting the future, and we'll see that. But then, is that sample sequence that you got, so what the spider actually computed was R1 plus gamma. My gamma and my R look alike, okay? R2 plus gamma squared R3 plus gamma raised to 4 3 R4, right? So this number that she gets, is that really what she can expect to see every time she goes to 3? No, that's a random variable, right? Because it's the sum of a sequence of samples. So that itself is a random variable which is a sum of many, many, many terms. But over many runs, that's going to have an average. There's an expected return at every corner, right? And what Flider really wants is to find the expected returns from each of these corners so that she can choose the corner with the best expected return, right? We're going to give that term, that expected return, expected discounted return, a name. We're going to call it the value of the corner. So everybody get an idea of what this value business is, right? So the value of a state is the expected total discounted return when the process begins in that state. So when you say the state at S0 is that state S, then so it's the expected value of the return when you begin at that state, and doesn't really matter when, at what time you begin at that state. From that point on, because the underlying Markov process is, the whole process is kind of has got some kind of consistency, you expect it to always be the same. So we can simply write it like so. Every state has an expected return given that the process began at that state, right? This is what we will call the value of the state. But then, when you're computing the value of the state, you have to be very careful. Let's go back to this problem, right? The spider doesn't lose any calories for walking down any edge. So this is a spider of infinite patience and infinite energy, right? If the spider starts at corner 1, how much is she going to get in the end? Eventually she's going to get to the fly, right? What about at corner 2? She's still going to get the fly. 3, 4. You guys are the back. What will happen if she starts at 5? She will always get a reward. And what is the value of that reward? 1 fly. So what is the value of every corner over here? 1. Do we need a discount? Because the spider is not losing anything, right? You're guaranteed that eventually, regardless of where you start from, you're going to get a reward of 1. So in this case, the value of every corner is going to be 1. That is the return, expected return from every corner. And now the spider doesn't really care where she lands, the fly is not moving, right? But then, so the expected return from every corner is 1 now, which means that the value of being at any corner is 1 for all the corners. She can expect to get the fly from everywhere. Now let me change this a little bit. Now my spider is hungry and she's burning calories. Okay? We know the transitions. Every time she walks an edge and gets to another corner, she's burning 1 calorie. So she gets a reward of -1. And the fly is going to give it whatever, any number of calories. Let's call it 1, right? So in this case, what is the expected reward if she starts at corner C1? What is the expected return? This should have been return, yeah, if she starts at C1. I'm going to give you the same transition matrix as before, 1/3, 1/3, 1/3, okay? What is the expected return if she starts at corner C1? Hira? Anybody? Expected return? No, because that's the immediate reward, right? But it's a return. Is it 0? You know what? Are you sure? You have seen this problem before. Okay? Let me write these expected returns as the values so here let me say the expected return is this is the value of being in or starting in state 1, see a corner C1, right? Can I express this in terms of the values of the other corners? How?
Discount times
That, okay, so suppose I don't discount over here, what would it be?
sum of values of the corner.
Okay, give me the formula. What is V1? Just because she landed in V1, she's always going to have to walk one edge, correct? V1 doesn't have the fly. So she's guaranteed a negative reward of 1, right? And then afterwards, with 1/3 probability, she goes to corner 2 and gets the reward there, gets a return over there, correct? And then she goes with 1/3 probability to corner 3 and with 1/3 probability to corner 4. So I can express the, remember, because the return is counting everything all the way into the future, correct? So the return at 1 is going to be whatever she lost or gained over there, plus the average over the returns of the immediate neighbors. You look puzzled? No? Okay. So because 1/3 of the time she's going to go here, 1/3 of the time there, 1/3 of the time here, right? It's expected over all the runs. Make sense to everybody? How many such equations will I have? I'm assuming no discounting, okay? If I assume discounting, how would I change this? I'd have a gamma over here, right? If I assume discounting, that I'm going to discount the future by some gamma. But if I don't assume discounting, it's just going to be that equation. And I have 8 corners. I'm going to have 8 such equations. Only one of them has a positive reward. The rest of them have this -1 plus blah. I can solve, can I not? 8 equations, 8 variables. Does this look familiar? This is exactly what we did when we were computing the life expectancy of the fly. It's the same equation, right? This is the Bellman equation, okay? So I can just say RC8 is 1. Basically, I can write down here if I assume gamma equals 1, this is the set of equations you can solve for all of these variables, and you're going to get the answer. Now, let's take this away from just one fly and make it more generic. There are flies in every corner, okay? And the expected reward after arriving at any corner is whatever, RCX, right, which is the average size of the fly there minus the travel penalty. And I'm going to assume now, okay, this is a corner, this is a cube where she can keep traveling infinitely, okay? How would I compute the return for every corner? So the return for every corner is going to be whatever the expected reward at that corner plus the average of what is going to happen immediately afterwards, right? If I show you the equation, maybe you will see it. I can write that? Yeah? Same thing. We have not really changed anything. All we added, this is still the same equation that we had in the past. We're just discounting by this gamma because we want to trust the future one step less, right? Each time. We're just discounting the future. Make sense? So this equation over here is what we will call the Bellman expectation equation. Again, going back, the return, the discounted return at any time t is going to be the sequence of the sum of the sequence of rewards, where you keep weighting things down by this gamma term as you go into the future. And the value you're going to assign to any state is going to be what is the return you would get, you expect to get if you started from that state, which is going to be the expected value of g given that you start from the state. And for that, you get this. So we are speaking in terms of expectations, and the expectations that we saw up there, this is the equation we just wrote. This is going to be the reward at that state itself, the expected reward at that state. Now we are speaking in terms of expectations, not samples, right? Again, I'm assuming that you know the distinction between expectations and the actual samples, right? So this is the expected reward at that state plus the discounted average of the returns in the neighboring states. Everybody clear about what I'm talking about, right? This is the Bellman expectation equation. Now, I said there was a second reason for discounting, which was more important than the fact that you just don't trust the future. And let me go back to this fly, okay? Suppose the fly can keep wandering, and if I didn't discount, if I just kept adding these things up, what is that sum going to be? Infinity. What's the sum going to be from corner 1, corner 2? Every single corner is going to have infinite return, right? You can no longer do any math. To make things tractable, you really want to be discounting the future. And so the only constraint you have on how you discount the future is that the sum of discount weights must be finite. The sum of all of the AIs that we saw must be finite, so that when I take a discounted infinite sequence and I sum it up, I get a finite value. It just turns out that using gamma raised to k, it gives you a very nice, beautiful discounting term, which sums to something nice and convenient, 1 over 1 minus gamma, right? You can use other things. You can use any kind of sequence which sums to a finite number, but then the math is going to be somewhat more ugly, okay? But then here's what I can do. I can write my Bellman expectation equation in this manner. I can say the value. So if I put the values of all the states in a vector and the expected reward for all the states in a vector, then I can say the value equals reward plus gamma times transition matrix times value. That's basically what the equation was. If you look at the equation on top, that's a set of simultaneous equations. The one with the summation, I can write it in matrix form. And so all I've done is write it in matrix form. Once I write it in matrix form, it just becomes V equals R plus gamma PV. Can you solve for V? It's trivial, right? It's totally trivial, because if I just write it out like so, then there's no more magic left to it. I can just skip all the text. I can just write this. V equals 1 minus gamma P inverse raised to times R, which is the vector of expected rewards. So it's very simple, straightforward. There's a problem with this. If you have 10,000 states in your system, you're not going to be able to invert that matrix. If you have 100,000 states, you're going to be able to invert it even less. Yeah.
So is dynamic programming actually much faster than this? Or?
Yeah.
And then what about value iteration and policy iteration?
We're going to get to this, right?
Oh, okay.
So, but we're just sort of explaining where the arithmetic comes from, right? So everybody with me so far? And so I gather you've understood everything about Markov reward processes. Then I'm going to make this one more. I'm going to take one step further. We haven't yet introduced, so far, we claimed that the spider was random. The spider just landed in a corner and just blindly walked around, right? It was completely random. But is the spider really going to be random? If the spider wants to catch the fly, what is it going to do? If you're a spider and you see a fly, what do? Yeah. You go to the fly, right? Are you going to travel randomly? Yes or no? No. We are assuming, so far we've assumed the spider had no agency. It was random. It had no control over its actions, right? But in the real world, the spider is going to take an action, right? And you, if you are the fly and she's coming towards you, what do? You run away, right? The environment changes. And these are things you actually want to factor in, right? So that gives us the Markov decision process. We have assumed so far that the agent behaves randomly. It has no agency. We have also assumed, so let's make the agent more intelligent. I'm going to give the agent the ability to decide which way it's going to move. The spider now actively chooses which way to move. It takes action, and ideally it's going to try to get to a position where it can catch the fly. But then, she's clever too, right? Every time the spider comes towards the fly is going to jump. So the agent's actions change the environment. Suddenly this very simple system became very complex, right? Or did it? It actually didn't. It stayed exactly as simple as it was. And that's the beauty of the whole thing. So here's how we're going to define it. The spider actually chooses which way it's going to move. These are all the actions that the spider can take. And the agent takes an action. And the fly is going to respond. And let's see how we actually model the system, right? First, I'm still going to have to assume some, if it's a completely malicious fly, and it's deterministically clever at escaping the spider is going to die, right? And you're never going to win any rewards. You're never going to get home. You're never going to win your lottery ticket. You're never going to make any money in the market. You're never going to win a game of chess. But that's not how the world is. There's a certain degree of randomness in it. So we're going to let's look at it. Each time the spider moves in any direction, the fly randomly jumps. But the fly arrives at a new state, which arrives at a new corner. It depends on where the fly jumped, which depends on which direction the spider moved. So the spider's actions modify the state transition probabilities. But now here's where I'm going to introduce unintelligence in the system again. You don't need to, but let's say I have this corner and my fly is sitting over here, and my spider, who's over here, walks up here. So the fly recognizes that the spider is moving towards the fly. It's going to jump. But when the fly jumps, it's not going to just jump deterministically. It's going to randomly land at one of these three corners with equal probability. Okay? So now the environment has been basically modified into the response of the environment has been put into the fly, right? When the spider moves towards the fly is going to jump and it's going to land at one of the adjacent corners. But if the spider is moving away from the fly doesn't jump, right? There's no reason for the fly to jump. Okay? So in this kind of system, how do I define the state transition probability matrix? And this is a trick question, right? If you just looked at this box and you tried to model the system and try to capture all of the dynamics of this process, you're not going to succeed. You're going to have to redefine the notion of state and action for this thing to work. But once you redefine it, once you define it properly, everything just falls out very cleanly. So let's see how I'm going to define it, okay? There are, in fact, not 8 states. There are only 4 states in this system. Again, this is based on the objective of the system, not on the shape of the cube, okay? What is the objective of this objective here for the spider? To catch the fly, right? What are the 4 states? It's caught the fly. It's 1 step from the fly. It's 2 steps from the fly. It's 3 steps from the fly. That's it. There are no more states, correct? So if I define it like so, then what about the actions? Does the spider have many different actions in this setting? No, it has only two actions. It either gets closer to the fly or gets farther from the fly, right? So we took the same system, but then we sort of redefined it to fit our requirements. And the definition is still complete, it's still accurate, everything is still perfect, right? Nothing really changed as far as the objectives are concerned, but then here's what happens. This is going to be a new Markov process. There are 4 states, S3, S2, S1, and S0. And if the fly were not moving, this is what the actual Markov reward process is going to be. If the spider has caught the fly, it's not going to move from there. So if it's in state S0, it's going to remain there with probability 1, right? If it's in any of the corners, which is exactly a distance of 1 from the fly, then observe that in each of these corners there's only one edge going to the fly and 2 edges going away, right? So with a probability of 1/3 it goes to the fly, with a probability of 2/3 it goes to S2. You see how that happens? Yes or no? Just think about this, right? So let's say the fly is here. Which are the S1 states? This is S0. This is an S1 corner. This is an S1. This is an S1 corner. This is an S1 corner, right? If the spider is in any of these 3 states, what is the probability that it's going to decrease the distance? This is 1/3, this is 1/3, and this is 1/3, right? So with 2/3 probability, it's going to increase the distance. With 1/3 probability, it's going to decrease the distance. So if the spider is in S1, with a probability of 1/3, it decreases the distance to, it goes to S0. With a probability of 2/3, it goes to S2, right? What about if the spider is in S2? What happens? So now which are the S2 states? That's going to be this guy, and this guy, right? Here, 2 out of 3 moves make it closer to the fly. So here with the probability of 2/3, it goes from S2 to S1. With the probability of 1/3, it goes from S2 to S3, right? And if it's in S3, it has no choice. It has to get closer to the fly. So with the probability of 1, it goes to S2. So you see the new slightly modified transition matrix. I reduced the number of states from 8 to 4. Makes things a lot simpler, as you will see, right? And now I'm going to introduce the notion of action. So again, everybody with me so far? Nothing confusing, right? I'm introducing the notion of an action. The spider can get closer to the fly, or it can go away from the fly, okay? And so here's the behavior of the fly. If the spider is moving away from it, it has no reason to fear. It doesn't do anything. If the spider is moving towards it, it jumps. Now flies are stochastic little machines. They jump. They're not going to land at the same corner. They're going to land at one of the other corners, but they're all equally likely to land at any of the 3 other corners. Okay? So now what happens? If the spider is, let's ignore the text. Let me draw this with a figure, right? If the spider is at state S0, it doesn't basically game over. The fly is eaten. So that we can ignore. If the spider is at state S1, if it moves towards the fly, what happens? The fly jumps, right? And where does it land? So the spider is here. The spider is here. It moves this way. The fly jumps. Where is it going to go? Here, here, or here, right? what is the end result? How far is it from the spider? 1, right? So in state S1, if the action is to decrease the distance to the spider, the probability of going with probability 1, the system stays in state S1, right? If it is to, but if the spider moves away, what happens? The fly doesn't move. With a probability of 1, you went from S1 to S2, right? So look at what happened. Depending on the action the spider took, the transition probabilities changed. Make sense? Right? It's very clever. We are not doing anything fancy. All we did was explicitly formulate the problem, right? Shankai, looking, yeah. So now what about if the spider is in S2? So if the spider is over here and it moves towards the fly, what happens? The fly jumps, and with probability 1/3, it's going to land on the spider. With probability 2/3, it's going to go away from the spider, right? But because the spider has already decreased the distance, the net distance in 2/3 of the cases is going to stay the same. In 1/3 of the cases, it's going to end up being eaten. So over here, if the spider moves towards the fly, when the state is S2, with a probability of 1/3, it goes to S0. With a probability of 2/3, it stays at S2. Correct? What if the spider is moving away from the fly? The fly doesn't move. It deterministically changes from S2 to S3. Right? And what if the spider is at S3? The only thing it can do is it has only one choice of action over here. It doesn't have the ability to go away from the fly, correct? And so here the spider is going to move towards the fly, so it's going to try to decrease the distance to 2, but the fly will jump. 1/3 of the time it's actually going to move away, but 2/3 of the time it's going to get closer simply because of the setting. So now with the probability of 1/3, the system stays in S3. With the probability of 2/3, it actually goes to S1. Right? So you see what happened over here? Depending on the action that the spider took in each state, the transition probabilities changed. And magically, just by doing this little trick, we have suddenly made the process tractable. Clear, Akash? Yes, see? So here's what we did. Now observe that what happened is we said that the agent's actions changed the transition probabilities, and the system changed. The actual transitions are from the environment. So now the environment has a transition probability over its states, but because this is the fly, the environment in this case is the fly, right? And the environment's transition probabilities depend on the actions of the agent. The transition probabilities are action dependent. Right? Okay. This happens all over the place. So this gives you this explanation, this expanded new model, which is called the Markov decision process. It's a Markov reward process where the agent now has agency and has the ability to decide its actions. We're going to represent individual actions. Remember, in our case, there were 2 actions that the spider could take. So we're going to represent each of these actions by the symbol A, and the action at any time t as AT, just for notation. The agent's actions affect the environment's behavior. The transitions made by the environment are functions of the actions. The rewards returned are also functions of the action. Okay? So here is the Markov decision process. It looks a whole lot like a Markov reward process with 2 major differences. First, the transition probability matrix is action conditioned. It depends on the action that the agent takes. And then you also have a set of actions. So first you add to the Markov reward process a set of actions that the agent can take, and then modify the transition probabilities to make them dependent on the action. At every state you have many choices of transition probabilities, as many choices as there are actions. Okay? And now somebody mentioned policy. You? So we're going to introduce the notion of a policy. Okay? The policy is the probability, is again, I'm being formulaic, but when we look at our example, you'll see exactly what happens, right? The policy is the probability distribution of actions that the agent may take at any state. So if I'm in any state, the agent is going to choose some action, right? Our spider may either try to go closer or try to go farther away. And instead of being deterministic, the spider may say, I'm going to be a little bit random because I'm going to explore. So the probability distribution of actions is the policy. This is something, so observe the transition probability is a property of the environment. The policy is a property of the agent. The transition probability is the fly's business. Whether it's going to get closer or further away is the spider's business. So you see the distinction, what comes from where, right? So the policy could be deterministic. I'm always going to decrease the distance. I'm always going to increase the distance. So let's take an example of a policy over here. Assume the fly doesn't move, right? So the spider is going to say, anytime I'm at C2, I'm going to go to C1. Anytime I'm going to go to C1, I'm going to go to C3. Is this a good policy? Not really. It's a horrible policy, right? But it's a policy. And so also, now in this policy, what are the transition probabilities? Again, the transition probability doesn't depend on the policy. It only depends on the action. The transition probabilities are the business of the environment. The environment has no clue as to your policy. It's responding to your actions. So the transition probabilities didn't change just because the spider has chosen a policy, right? But the policy will change what the reward that the spider gets, and we'll see that. So the transition probabilities depend on actions, not on policy. Now suppose here's another policy, right? This is a different kind of optimal policy in the sense that the spider is always going towards the fly, right? It's still a policy, but the spider is going towards the fly. So now, so the expected return that you get from any state is going to depend on your policy, because the return depends on the action, and the action depends on the policy, right? So you have this interesting combination. You have the transition matrix, which depends on the action but not on your policy. You have the return, which depends on your policy. And if the distinction is not clear, let's take a look at this. Let's go back to our favorite guy, right? Suppose this guy has this policy. He's always going to decrease the distance to the fly, right? What is the expected return at any state? Will he ever catch the fly? Take a look. Does it ever transition to S0? So let's say, unless he begins at S2, he is not going to catch the fly, right? If he begins at S3, is he ever going to catch the fly? From S3 he goes to S1, from S1 he stays at S1. He is so screwed, right? Is this a good policy? What is the expected return for this policy at S3? 0 or minus infinity, depending on whether it's dying or not, right? What is the expected return at S1? 0. What is the expected return at S2? Eventually it's going to catch the fly if you don't use a discounting, right? The only condition under which it's going to catch the fly is if it's at S2. So you see, the return depends on the policy. The transition matrix depends on the action. You see the distinction? Right? Let me give you a different policy. This guy. Is this a good policy? It's a good policy, right? At S3 it's going to go to S1. At S1 it's going to S2. At S2 it has a 1/3 probability of catching the fly. If I don't use a discounting factor, what is the expected return for S1? S2? S3? 1. It doesn't matter where it starts. This is a good policy. It's going to catch the fly. Right? So you see how the return depends on the policy and how the transition matrix does not. You guys at the back? Makes sense to you, right? You also see how a greedy policy is not a good policy. If it's deciding that it's always going to try to decrease the distance to the fly, most times it's going to starve to death. So anyway, you can also have a stochastic policy. You say that every state, half the time I'm going to get closer, half the time I'm going to get farther, or 1/3 of the time I'm going to get closer, 1/3 of the time I'm going to get farther, right? In this case, now what is the actual transition matrix? The transition matrix is going to be a weighted combination of, for every state, the transition probabilities are going to be a weighted combination, right? Because the entire thing is stochastic. You've injected the agent stochasticity into the environment by making the policy itself stochastic, right? That's about it. So now let's go back and look at the value functions, okay? What is the value function I have? The value function equations I wrote, they are still going to stay the same. They don't change, right? So in this case, the value for state S1 is going to be the rewarded state S1 plus gamma times the value for state S1, because that's the only state it's going to go to, right? Because this is the transition matrix over here for this policy. So also, if you're in state S3, then you can either go back to S3 or S1. So this is going to be the equation for the value for state S3. This is exactly what we wrote earlier, right? And this is going to be the equation for value for state S2, right? And observe that this value function depends on the policy. If I chose the other policy, the value functions for the two lower states didn't really change, because here you're still going closer, but the value function for the guy at S1 changed. The function changed, right? Simply because you have a new transition matrix. And if I have a stochastic policy, the value function is going to be an average of the two. So if I'm doing something like this, if I'm going to take a minus 1/3 of the time and a plus 2/3 of the time, then I'm going to have 1/3 times the equation for the value function for the value function obtained from this transition matrix, plus 2/3 times the value function obtained from this transition matrix, right? So you're just sort of mixing. You get the idea. Now, the interesting thing is none of this is particularly complex. It's all very straightforward, very basic probability. What was the key? The key was not in the math. The key was in posing the problem just right. You have to set it up. And once you set it up, everything is very straightforward, right? It's beautiful. Now, so we're going to call this the state value function of a Markov decision process. The state value function of a Markov decision process is the value that you're going to assign over to a state across all actions. And this is going to be a function of the policy, right? The policy decides with what probability you're going to choose what action. For each action, you're going to have a corresponding transition probability. So what you would have here is this guy is the value that you got for this specific action A. You weighted this across all of the actions. The probability of an action came from the policy. And so this is now the value that you're going to assign to being in each state based on the policy that you have chosen. So you say, here is my policy. This is the policy I'm going to follow. For this policy, what are the values of the various states? And it's just, wait, question marks on the faces at the back? No? No? Are you sure? That wasn't a very convincing nod. Okay. So, but you get what do I need to explain this equation? There's nothing magical about it, right? But then observe that this thing is actually averaging over all of the actions, correct? I can also assign a value to a specific action. I'll call this the action value function. So the action value function are the terms that you get. If I choose an action of getting closer, what is the value I have for the state? That is very action specific. So I'm going to call that the symbol Q. It's the action value function. The state value function is averaging across all actions over the policy, right? And so I'll just sort of summarize this over here. This is where I was supposed to be at the end of last class, and unfortunately we're kind of a whole class behind. So I can give you the action value function for a state, which is basically the equation on the board, on the slides, but we've already seen exactly where this comes from. For an action, again, we're going to assume that the reward is action dependent. In the case of the fly, the reward was not action dependent. It only depended on which corner you ended up in. More realistically, the reward is going to be action dependent, right? But it's going to be the action dependent reward for the state plus, now observe something interesting over here, right? If I have a policy, when I'm at this state, I am not making any claims about what action I'm going to take at the next instant, right? So the action value function is going to be the reward of the current state plus the weighted sum, the average of the state value functions at the next state. That's how we defined it, remember? That the value of the state is going to be whatever reward I got over here plus the average of all the neighboring states. And there, when you're speaking of the value, you're not really speaking of the action you're taking in the next state. What is the value of the neighboring states? So this is just simply saying that Q is the sum of the local reward plus the average of the state values of the adjacent states, and this guy, and V is basically the same thing averaged over all states. But then when you put them all together, you get this interesting combination of equations where I say that the first equation is the equation that I just wrote first, which is every action has its own transition matrix, and so you have an action dependent value, and then you're averaging over all of these actions, right? So the state value function over here is simply going to be, very clearly, the state value function is simply the weighted average of the action value functions. Each action has its own, each action gives a different value to the state, and you're averaging over all actions, where the probability of the action depends on the policy, right? And if I just plug this term into the equation above, you get an equation that relates state action values to state action values. Now, this math, I'm not going to try to explain it. It's very obvious. I can twist my tongue around and tie it into a knot trying to explain it, or I can just leave it on the slide. So what I will do is leave it on the slide, and we'll harass you with quiz questions, right? So that way maybe make sure you get it. And so these are the Bellman expectation equations, the Bellman equations. You have two Bellman equations. One which computes state values based on state values, and one which gets state action values based on state action values. They're both called Bellman equations, right? Bellman expectation equations. There's a different set of Bellman equations we'll come to. And so when I speak of computing a Markov decision process, what we are really saying is I give you all of these properties. I give you the transition matrix. I give you the probability distributions for rewards. I give you a policy. What is the value of each state, and what is the value of each state action combination? Computing all of these is called computing the Markov decision process. It's basically solving these two sets of equations, right? And we know how we can solve these two sets of equations. Very simple. For the state value, to compute state values, you can just write the whole thing out as a matrix equation, and you have a simple matrix inversion which will solve it. And unfortunately, if I have a large number of states, so how many states in a chessboard? Anybody know? 10 raised to 120, right? So if I have 10 raised to 120 states, how large is that matrix going to be? 10 raised to 240. How much time to compute its inverse? Not before the universe ends, right? So this is not going to be tractable. Now, again, these functions, right? So, but then things get even more complex. Although we know when you look at spiders and flies, it looks very simple. We saw how I can actually compute the values for all the states given a policy. But what's the problem I really want to solve? Find the optimal policy, right? How would I do it? I'm going to have to compute the state values for every policy and pick the policy for which these are highest. And that's not a tractable problem, right? So again, all of these are very easily solvable, but then there's a notion of for optimal policy that's going to be the policy that maximizes the expected total discounted reward at every state. And there's a policy ordering definition. This is a little bit of math that I'm going to just close the lecture with. It turns out that for all of these processes, there always exists an optimal policy. And how is the optimal policy defined? An optimal policy is a policy such that the value of every state under that policy is always going to be at least as large as the value for that state under any other policy. So if the value for even one state is lower than what you would get using any other policy, that's not an optimal policy. And you can prove that such a policy exists, right? So basically what we mean is if I have S1, S2, S3, S4, I have pi 1, pi 2, these are all different policies, right? I'm going to have some value here. Each policy is going to assign some state values for all of these states. If this is my optimal policy, then it means that this guy is greater than all of these fellows. This guy is greater than all of these fellows. This guy is greater than all of these fellows, and this guy is greater than all of these fellows. If this doesn't hold for every state, greater than or equal to, if this doesn't hold for every state, it's not an optimal policy. And the proof is that such an optimal policy always exists. And so that's something called the optimal policy theorem. I suggest you actually look up the next several slides through the backup diagram, because we're going to be talking about these things in the quiz. And we'll dive in the next lecture, right? So 10 slides, which are your responsibility. There will be 10 quiz questions, one from each slide. And if you're watching, you know what you're getting, setting yourself up for. If you're not watching, good luck with the quiz. Thank you. Yes?